Okay. Can you all see the screen?
Yes, sir.
Okay, I think there is a little delay in displaying the screen. Okay, so Bismillah ar-Rahman Rahim. Welcome to this course, the fundamentals of earthquake engineering and the seismic design. So as you know, this is a special topic. So the code is CE5190. It's mainly a course for structural engineering, but also for students in the earthquake engineering can also consider this as a special topic and as a minor subject. Okay, so let me start with the first lecture regarding this course. So you know that the credit hour for the course they are 03. So let me just mention some of the basic details about the course and regarding the examination schedule and so on. So you already know the title of the course is CE 5190. It's really a very basic subject. That's why we call them as fundamental. Fundamentals of earthquake engineering and the seismic design. Okay, the typical lecture delivery will be like this. That I'll be using this whiteboard with my pen, and you will be shared with the video recording as well as with these lecture slides that you can read at your home for preparing your lectures and preparing for the examinations. I think there is some problem. I can see some interruption, but let me just check this. I will come back. So I think it's okay now. Okay, so as was I was mentioning here, the credit hour for the course will be 03 hours, and the same way the contact hours they are 3 hours. The lecture, as we have decided, always we will have a lecture on Friday. Okay, and the class will be from 2:30 to 5:30 p.m. Okay, but what we'll do in the class that there will be also a time for the break, 15 minutes. So this is the typical policy of our department. So we will start, let's say, around 2:30 up to 3:45, and then we will have a break. It will be from 3:45 to 4:00. That will be for the break, and from 4:00 to 5:30 will be the remaining class. Okay, so what is important more for this course to just note down some schedule of the activities. For example, the midterm. So as the department has decided that the midterm will be carried out in the time window of 14 to the 20th April. Sorry, 14 to 12th of the May 2021. And the final term we have to take around 16 to 22. So this is not May, I'm so sorry. This is June, I think. Okay. So this is June, and this is August. Okay. So August 2021. And we will share the result with you around 23 to 29 August 2021. Okay, so these are the dates that you should keep in mind for the course. Okay, so what we will do is to have around 7 lectures, maybe 6 or 7 lectures before the midterm. Let me just write here. So what we will do for the lectures, I think we may have up to 1 to 6 or up to 7 lectures before the midterm. And then the remaining 8 lectures. So there will be 8 lectures after the midterm, and then we will have a final. Okay, before the midterm, we must have a 1 week prep. So I will give you 1 week time to prepare for the midterm. Okay, and before the final term, you will have 2 weeks to prepare for the exam. Okay. So over all these lectures, these are around 14 or 15 lectures in total. And we will have classical lectures related to the subject. Okay. We will be having quizzes. So as per the CLOs, we have to take 3 quizzes. Okay. And we will have 3 assignments. And there is one midterm, one final term, but also there will be one CEP, the complex engineering problem. So before this midterm, we will have in the last lecture, maybe in the 6th or in the 7th lecture, we will discuss the CEP, what you're doing in CEP. that one half lecture, one lecture will be dedicated to CEP, and then we'll be working on it over the all the weeks till the final term. And once the final term is taken, then you will present your CEP results. And before the final term, we will have a lecture here that will be dedicated to the CEP discussion. CEP discussion. So we will have a complete lecture where we will discuss various aspects of the complex engineering problem. And the rest we will have all the lecture related to the course. Okay, the criteria is for the grading. So I think you are familiar with this, that we will have sessional, which are 25%. We will have the midterm that is also having a 25% contribution. And the final term has a contribution of 50%. Okay, so this will be the typical grading criteria. In sessional, again, it is distributed as in quizzes, assignment, and CEP. So we will have a large portion of the score contribution from the CEP, and then quizzes and the last assignment. Okay, because we can see that there is a lot of chances for copying. But let's see. Now we are starting with the online classes. Maybe in the future we can have some physical classes as well. But we'll look at the policy of the department. Okay, so let me start now formally with this lecture number one. This lecture is related to the elastic response spectrum. I will share with you the content of the course as well through the Google Classroom, so you can have a look at the various topics that we are going to cover. But before I start with the actual topic of this course, I have to share with you some information related to the elastic response spectrum and its history. So mainly the it's like the history of this concept, elastic response spectrum. And we will see that elastic response spectrum is very important when we are dealing with the seismic analysis and design of structures. And the history is important because all the new concept that we are dealing with in the modern time, in today time, is all built on the past concept of those researchers and scientists who work in this particular topic. Okay, so what I'm going to do in this lecture is basically to present some of the seminal concepts in earthquake engineering and structure dynamics. So this lecture is basically giving you idea and background about the seminal concepts. Let me write here, seminal concepts. Okay, seminal concepts in earthquake engineering and structure dynamics. These are called a seminal concept because all the later development and all the code and standard that today that you see in all the analysis procedure basically these concepts. So they are developed based on these concepts. So these concepts were really the foundation of all those developments. So what I will be discussing is to look at the origin and the early developments of the elastic response spectrum, because elastic response spectrum is really the backbone of the structure analysis, because when we are analyzing a structure or designing a structure, we need the elastic response spectrum for which we design the structure. So we'll talk mainly about the origin and the early developments. But the origin and the development till the 1960s, okay? So right from the beginning up to the 1960s, what efforts were made in the development of the elastic spectrum will be discussed in this class. These are important to understand because sometimes we are using many things in earthquake engineering, in the seismic design, and the structure dynamics, but we do not know where it comes from. So this is very important to understand how these things were developed. The elastic response spectrum, I think majority of the students, they are already familiar with this. They work on this and they know uh, this particular curve that we will see in a minute during their BSc courses, during their MSc courses, because some of the students are already taking a lot of MSc courses. So the elastic response spectrum, it basically summarizes the peak response of all possible linear single degree of freedom systems to a particular component of ground motion. So when we look at the elastic response spectrum, right here, elastic response spectrum, so it mainly gives you the peak response. What is the peak response of a single degree of freedom system? Peak response of we will see in a minute what is a single degree of freedom system to a particular ground motion. So this is the peak response of SDOF systems to a particular ground motion. Okay. So it's like the elastic response spectrum is like a kind of an envelope. It gives you an idea what will happen to a particular single degree of freedom system if you subject it to the ground motion. It also provides a practical approach to apply the knowledge of structure dynamics to the design of structures. For example, if you have a response spectrum, so it developed based on the dynamic analysis, but once you have it, on one hand, it can facilitate the analysis and design of your structure, because in modern time, what we do is that we divide this problem into two activities. Like on one side, we develop what is the response spectrum, and on the other side, we carry out the structure analysis. But in reality, when there is earthquake, so earthquake excitation and the structure response is a coupled thing. It is happening at the same time. But for the facilitating the design, we consider these two as two separate things, and we deal them separately to basically facilitate the design procedures. So understanding the concept of the elastic response spectrum is very important uh, uh, for the practical approach and to apply the knowledge of structure dynamics for the design. So mainly, it's important for the structure design, I should write. Now, let me just give you some background of the response of single degree of freedom system, because the elastic response spectrum, their development is all based on how a single degree of freedom system behave when it is excited. Okay, so by single degree of freedom system, we mean, for example, if you have a single story frame, let me just write here. Okay, let's say I have this one story frame. It is having flexible column, and it is having a huge mass that is supported by this column. Okay, so if during the earthquake, if it moves laterally, what will happen is that this is how it will deflect. Okay, and this mass will move horizontally in that direction like this. Okay, so let me just put here that this is representing the side movement or the side displacement of this mass M. Okay, so this is a one-story frame example. Or what we can do is, if we uh, look at this problem from a mechanics point of view. So, for example, there is like a mass, a huge mass. Okay, that is rested on these rollers. Okay, this is the reference frame. And this mass can move laterally with this displacement u, but the movement of this mass is basically restricted by a spring system here and also by a dashboard or a damping mechanism here. So the same problem can be idealized with this mechanical model as well. So the equation that govern the deformation and basically the relative displacement of a linear single degree of freedom system subjected to a ground acceleration. Uh, let's say the ground acceleration is UGT with double derivatives. So if these systems are subject to ground acceleration, there is a time variation. So if you look at the relative deformation of the system, displacement is equal to minus ground acceleration with time. So this is the actually the dynamic equation or the solution of the equilibrium problem for the dynamic, and this equation can be solved to look at the response quantities like the displacement here, velocity response, and acceleration response of the system. Okay, if you look at this equation, what you can see, for example, if I'm interested in this displacement because the mass is moving laterally here, it is moving laterally here, and if I'm interested in this displacement, what is the deformation response of the structure? So for a given ground acceleration, the deformation response of the system will depend on the natural vibration frequency, that is the omega n. So U basically natural vibration period. So we see that omega n is equal to 2 pi f, where omega is the vibration frequency, the circular vibration frequency, and f is basically the cyclic frequency. Or we can mention it in this form like 2 pi over t, tn, fn, because these are natural time period, natural frequency. So the displacement will depend on the natural vibration period or the natural vibration frequency. What? Stubborn. And it will depend on the damping ratio. So how much damping is there in the equation. So finally, if I write here that the displacement response of this single degree of freedom system is approximately equal to the displacement that is the function of time, the natural time period of the structure, and the damping ratio of the structure. So this is how the relative deformation or the relative displacement of this single degree of freedom system will depend on. Now, if we are looking at the response of a single degree of freedom system, and we mentioned about the peak values, so a plot of the peak value of the response quantity is a function of the natural vibration period. Okay, so let's say peak value of displacement. Okay, so this is a kind of a response quantity with respect to the vibration period, the natural vibration period Tn of the system, or a related parameter, for example, the circular frequency omega n, or the cyclic frequency, the Fn, is called as the response spectrum. So let me just mention here that the plot of peak value of displacement with respect to the, let's say, time period is called basically a response spectrum. And response spectrum can be plotted for displacement as well as for velocity as well as for the acceleration. So if it is plotted for displacement, we call them as displacement response spectrum. We can call them as velocity response spectrum or acceleration response spectrum, depending on which quantity you are looking at. Okay. Now, remember that each of these plot is for the single degree of freedom system, the one that we just described in the previous slide, which is having a fixed damping ratio, and it is several such plot for different value of damping can be included to cover the range of damping values encountered in the actual structure. So, for example, the spectrum is basically for the SDOF system, so you have to keep this in mind. SDOF systems that is having a range of time periods. So the time period ranges from some very low value, or let's say from 0 to some max value, and for a given damping ratio. So if you do that for a range of damping ratio, you can develop the spectrum for various cases of the structures. A variety of response spectra can be defined depending on the response quantity that is plotted. So as we mentioned in the first bullet here, there is basically a plot of the peak value. So how it is represented. So let me write here. So if I'm looking at the response spectrum for displacement, so it is a function of Tn and damping. So as I mentioned in the previous bullet, and it depends on the time period as well as the damping ratio, and it is approximately equal to the max over time, the absolute value of displacement, which was the function of time Tn and the damping ratio. So the response quantity was actually the function of time vibration period and the damping ratio, but the peak value is only the function of the time period and the vibration period and the damping ratio, because the time is now is ignored because we already took the max, so it's only the maximum value. The same we can obtain for velocity. Again, it is a function of the vibration period. Don't call this as time period, Tn. It's best to describe this as a vibration period. And the damping ratio, and again, it is the max over time of the velocity response that was dependent on the time, the vibration period, and the damping value. And now, the same we can obtain for the acceleration, which is a function of the vibration period, the damping, that is approximately equal to the max over time of the acceleration. There was a function of time Tn, the vibration period, and the damping ratio. Now there is a superscript T written here on the acceleration, okay, which means it is a total acceleration. Okay. Okay, so as I mentioned here, that in that equation we had the acceleration with a superscript T, that is basically equal to the acceleration, relative acceleration of the structure plus the acceleration of the ground. So whenever we talk about the peak acceleration, is basically the acceleration, the total acceleration. So when we draw the plot of the peak value of, let's say, deformation or the displacement response spectrum, it is a plot of T equal to U naught, and U naught, is what we just obtained here, is the peak value of the response of the single degree of freedom system. So this U naught, if we plot this U naught or D against the vibration period, we obtain the displacement response spectrum. And remember that this is for a given value of the damping. The typical case is that we draw this for 5% damping that describe the elastic response spectrum. We can obtain similar plot for the velocity. Again, the velocity is a relative velocity response spectrum. And also we can draw the same for the acceleration response spectrum. Let me just mention here that velocity we always write by the V, and acceleration is A, and this is the total acceleration. There is another term that is called as the pseudo velocity. So pseudo velocity response spectrum, again, you can even develop this kind of spectrum as well. And the pseudo velocity response spectrum is basically a plot of V defined by is V is equal to omega n into D. So when you develop the displacement response spectrum and you multiply the displacement response spectrum with a circular frequency, you can convert that spectrum into the velocity spectrum. And this velocity spectrum is called as a pseudo velocity spectrum because it's not the true velocity spectrum. That's why it is called pseudo. Okay, you can further simplify this as 2 pi divided by Tn into D. So again, if you plot this V as a function of vibration period for a given damping, you can have a pseudo velocity response spectrum. And this is these days is quite important for understanding the demand on structures. There is another important parameter for structure and the seismic demand. And there is a peak value of the strain energy stored. So what is the peak value? Peak value of strain energy. So when you have an accelerogram that is going to excite a structure, how much energy will be stored in that system if it is behaving elastically, that is equal to strain energy in that elastic system half mv square. Okay, and this is basically the kinetic energy of the mass m with respect to a velocity. Okay. The pseudo acceleration response spectrum. In the same way, it is written as A is equal to omega square into D. So if you develop a displacement response spectrum and you multiply that with the circular frequency omega n, and you take the square of omega n, you will basically convert the displacement response spectrum to pseudo acceleration response spectrum. And again, it's called pseudo because it's not the true acceleration response spectrum. We can further simplify this by converting omega to 2 pi Tn into d. And again, that this pseudo acceleration response spectrum, it will be for a fixed damping ratio. You can plot A with respect to Tn to have the spectrum. Now, the peak value of the equivalent static force or the base shear, so let me just write here static force. Which is that is basically the equivalent. We also call them as base shear. The base shear equation will be equal to VB, let's write this, VB and mass time the peak acceleration or the pseudo acceleration, because this is giving us the peak value. Mass time A, which is the second law of the Newton for the inertia. If we have normally what we do in codes and in the design that we convert, we write weight instead of mass. So what we have to do is that we have to divide A by G and then as W. So now we can use this equation as a function of weight, and A over G is basically giving us the percentage of weight. The base shear is a percentage of weight acting on the structure. Okay, here in this equation, you can see that W is representing the weight of the structure and G is representing the gravitational acceleration. The base shear is equal to the inertia force that, as I mentioned, associated with the mass undergoing the pseudo acceleration. So this equation is basically describing that the mass undergoing the pseudo acceleration is resulting in the inertia that is equal to the base shear. Okay, for a damped system, the A is not equal to, remember that A is not equal to the peak acceleration, which is the actual acceleration response of the single-degree of freedom system. Okay, and we will have a discussion about this based on the past research. But what is basically this is doing is that it is making our analysis and design simple as compared to looking for the actual response acceleration. So this was a little basic about the response spectrum, the elastic response spectrum, some of the important parameters which are used to describe the spectrum and do the analysis and design of the structure. Now some instrumental work that was carried out with regard to the development of the elastic response spectrum in the past. So let me mention here. Instrumental or intuitive approaches. So let me just say instrumental and intuitive approaches. So these are like the kind of first approaches and procedure to describe the elastic response spectrum. So the very first appearance of the idea of representing earthquake excitation by a response spectrum was in the 1926. There was a paper written by a scientist from Japan. So his name was Soehiro. This is how it is written, Soehiro. And it was in 1926. So this was the very first researcher who wrote a paper on the elastic response spectrum. Soehiro was at the time, he was the director of the Earthquake Research Institute. Earthquake Research Institute at the Imperial University of Tokyo. And he wrote this paper soon after the 1923 Tokyo earthquake. So it was after the 1923 Tokyo earthquake. He had an instrument that he called a seismic vibration analyzer. Okay, and this seismic vibration analyzer consisted of 13 compound pendulum elements. So there were 13 pendulum, and these pendulum were having different natural vibration period, and it was covering a range of time period or a range of vibration period from 0.22 second up to 1.81 second. So this was the compound pendulum of the seismic vibration analyzer. So what was the idea? That during an earthquake, each pendulum will trace its motion on a rotating drum to which it was attached, and in effect producing its deformation response. The peak value then give 1 point on the deformation response spectrum. So I think we all understand this concept that every pendulum was making its trace during an earthquake and on a drum. And that trace was then analyzed, the peaks were obtained for every pendulum, and drawing those peaks against the vibration period of the pendulum gives the elastic response spectrum. This is the same way that as we are doing today using various software. Now, this instrument anticipated by several years the development of response spectrum theory. The development of response spectrum theory. And you can say that it's the ancestor of the Reed gauge that was widely used for general shock and vibration measurement in mechanical engineering. Now, actually, this instrument, it recorded a number of weak motion later on at the time, but it did not record any strong ground shaking in the past. Okay, and in parallel, what happened? In parallel, there was another effort in the San Francisco. And in San Francisco, there was an office of the United States Coast and Geodetic Survey. So it was USCGS, United States Coast and Geodetic Survey Department. So what this department did is it also constructed an instrument with a large number of oscillators on the same principle of the Soy Hero, but again, this also did not record any strong ground shaking. Now it said that the state to which the Soy Hero instrument influenced the thinking of the early researcher in the United States is not known. So it's not really much clear and sure how much that principle was followed in the United States. But in the note, it's given that Soy Hero After his invention, he visited the United States in around 1931. So he visited the United States in 1931. And then he was invited by the American Society of Civil Engineers to deliver a lecture at a number of institutions. For example, the California Institute of Technology, that is called as Caltech. Okay, the Stanford University, and the University of California at Berkeley, UCB. So Hiro visited these universities to give a lecture on his own invention. Okay. Now, in parallel to Soihiro, there was another professor of seismology. His name was Binoy, written like this. And he presented the same intuitive idea, just like the Soihiro, that during an earthquake, each of series of undamped pendula with different natural frequencies would write its response seismogram. Okay, so what he called is the response seismogram. Okay, in plotting the peak response as a function of the natural frequency would give the deformation response spectrum, which he referred to as the undamped pendula spectrum. So he developed the same spectrum just like the Soihiro, and he called them as undamped undamped pendular spectrum of earthquake. Okay, now he sketched such a spectrum, and he also defined what is called as what he called as the seismic destructiveness. Seismic destructiveness. And then he obtained is the area under the spectrum and the area under the spectrum. This was equal to the area under the spectrum. In modern time, this parameter or this value or intensity is now known as the seismic intensity. Okay, this idea later on was extended by Husner in 1952 to compute the spectrum intensity for several accelerogram. Here. So after the Binov comes Husner, and Husner in 1952 computed the spectrum intensity, which was on the concept of the seismic destructiveness as mentioned by the Binov. So spectrum intensity for number of accelerogram. The Binov intuitive presentation of pendular spectrum and seismic destructiveness was presented in one of his papers. There was a short paper, and he also provided a presentation on his concept for the derivation of the deformation response spectrum based on that recent theoretical work that was presented by the Binov. So what he did is presenting his idea for the seismic destructiveness and also for the derivation of the deformation response spectrum. So let me mention here that the deformation response spectrum concept was also presented at the time. So this was regarding the instrumental activities carried out at the time for the development of the elastic response spectrum. Later on, there was also a theoretical approach. There was also was carried out a number of work related to the theoretical approaches. So let me just mention about those approaches which was based on the theory rather than the experimental work. So in 1930s, this was mainly happening in the 1930s in Caltech. So it happened in the 1930s in Caltech, the California Institute of Technology. And there were a number of professors there who work on this science. There was a professor from structural engineering. His name was, I think, R. Martin. And there was another professor from the aeronautical engineering department. His name was Von Karman. Okay, T.V. Karman. So these were the two professors who took interest in this science. And they took interest after meeting with Soihiro, and also there was another professor, Taku Neto, his name. He was also from the Tokyo University, where he delivered a lecture in World Conference in 1929. In parallel, Binov was also working on these concepts. So he was a professor of seismology. And there was another scientist, his name is Biot, who was a student at that time. And who was a student of both Martel and Carmen, who did some pioneering work related to the development of the elastic response spectrum. At that time, there was also a work by Rayleigh related to the theory of sound. So the concept of the theory of sound was, it appeared in 1877. And many scientists believe that even those concepts was enough to treat the mechanical vibration theory. And the same principle that was present in the Rayleigh book of the theory of sound was sufficient in principle to analyze any problem related to structure dynamics. Okay, but however, this was not made popular for the earthquake analysis of structures at that time. Now, this situation, the situation related to the theoretical approach in earthquake engineering changed in 1930 when Professor Carmen was delivering lectures on the wave motion and vibration. Okay. So he was mainly giving lectures on wave motion and vibration, and among his students was Viot, who took interest in this science, and along with the Professor Carmen, they collaborated and they wrote a book on those lectures. And those books, they played really an important role in the graduate education of students at Caltech. And among the other students who took interest were Husnul. There was another Hudson, Popov. These are some famous researchers and scientists who were students of Carmen and who took interest in the earthquake engineering. The basic theory, the mathematical theory of the response of system to arbitrary excitations, like the earthquake excitation, was completely laid out in 1932 in a PhD thesis of Biot. So, like you can say, he was the first to lay down the mathematical theory for the response analysis of single degree of freedom systems. Not single, there was also multi degree of freedom system, but also for the, you can say, for the response of the system. And he was a student of Carmen as well as the Martin. What Biot did is that he applied the model analysis theory to analyze the harmonics of the undamped shear beam. So he analyzed, what he did is he analyzed undamped shear beam. And that he took to idealize the multi-degree of freedom multi-story building. And it was studied analyzing it under the arbitrary ground accelerations. And Biot was also having the foresight, and he mentioned in his thesis that it is much more convenient to divide the problem and to analyze separately the elastic property of the building and the frequency distribution of the earthquake. So you can, you can look at his vision. So he was like proposing that we should divide the analysis problem into two parts. So one, to look at the elastic properties of the building, and also on the other side to look at the frequency distribution of the earthquakes. Like today, what we are doing is that we are looking at the vibrational period of the structure, and we are also weight of the structure, and also we are looking at the response spectrum from where we obtain the seismic demand on that building for design. Later in his work, what he did is that he wrote the excitation as a Fourier integral that was used to define the Fourier amplitude spectrum. So what he did in his work is to construct Fourier amplitude spectrum. And he expressed each model contribution to the response in terms of the Fourier amplitude spectrum for the beam. So these ideas were further developed and presented by Biot in his two papers. And he referred to the Fourier amplitude spectrum later on in his work as spectral intensity curve. Okay, after the Biot work, there was another, his colleague Hosner, who was like the student after Biot of the same Professor Martin in the earthquake engineering. What he did is that he continued the, he mentioned in his work that it is a continuation of the work done by Biot. And he applied the theory for model analysis of earthquake responsive system and studying both the shear beams and bending beams. So he studied beams both with the shear type response and a bending type response. So again, like idealizing multi-story frames and idealizing multi-story walls. But he also emphasized on the response spectrum rather than the Fourier spectrum as a more practical approach for the engineering application. So he more emphasized on the response spectrum rather than the Fourier spectrum. The work of Husner in his PhD also included plots of the pseudo-velocity response spectra, which they called as a V diagram. So they call it as a V diagram, was basically the pseudo-velocity spectrum, and he developed that for 6 ground motion, and that plot was produced using various mechanical or graphical methods. The concept of the response spectrum existed for quite long time after the 1930s, but it was further developed in the or more clarified in 1941 in 2 papers. The first paper was written by again by Biot, and the second one, the first was written by Husner, and the second one was written by Biot. So Husner in his paper defined the deformation response spectrum in terms of the Duhamel integral. So it was in 1941 when Duhamel integral was used to solve the equation of motion, and what he developed is the displacement frequency spectrum. And he also introduced the new standard notion for the equivalent static force that produces the peak deformation induced by the earthquake, and plotted this as a force frequency spectrum. So he proposed another spectrum which he called as the force frequency spectrum. Okay. These look like this if you look in a crude way. So it was like a period on this side, and it was a maximum displacement response on this side. And these plotted looked like something like this. This one he called is the displacement frequency spectrum. And then there was another spectrum that he obtained for, again, running period on the x-axis, and on the y-axis what he plotted is the A by G, the pseudo acceleration divided by G, and that looked like something like this. Okay, so the A by G is basically the amount of weight, and that is equal to basically the amount of base shear or the coefficient of the base shear for a given single degree of freedom system, and he developed it for the 1931 earthquake and including many others. The second paper was again in the same year written by Biot, and he attempted to draw a curve representing some kind of harmonic analysis of earthquake, where the acceleration intensity is plotted as a function of the frequency, and such curve was as an earthquake spectrum. Okay, so the same year was another paper written by Biot, and he called a curve is earthquake spectrum. Okay, there was flooding. The acceleration intensity is a function of the, so it was acceleration versus frequency. Okay, and he used a mechanical torsion pendulum in order to draw its response. Mechanical torsion pendulum analyzer. So he took a mechanical torsion pendulum analyzer and subjected it to uh, earthquake ground motion and recorded its acceleration response. But again, this was an undamped system. Okay, and he analyzed that mechanical torsion analyzer for a number of earthquakes recorded at that time in the United States. So it was 1935 earthquake, 1937, and 1938. Okay, so this was some of the theoretical work carried out in the development of the elastic response spectrum, where a major role was played by Bute as well as by the Husner. Now, what I will do is to take a break, and then we will continue by some of the development that was looking at the computation of the response spectrum using other procedure like the using the computer tool and the numerical approaches. So I will see you at around 4. Till then, we take a break.